Good morning, good afternoon, everyone. This is another problem of application of the relativistic quantity like momentum, kinetic energy, and total energy. So in this problem, we have an electron has a total energy that is 250 times its rest energy. What is the kinetic energy of the electron, and what are its speed and momentum? So let's start by question A. And the question A is asking the total energy is 250 times the energy of the electron. Now, we know that the total energy of a particle is equal to gamma mc squared, and mc squared is its rest energy, which is gamma E0. So, and we have we are given that the total energy is 250 times the rest mass or rest energy. So which means gamma is 250. Now the question is the kinetic energy. So we are not asking to calculate the speed, but we are asked to calculate the kinetic energy. We know that the kinetic energy is equal to the rest energy gamma minus 1, which in this case means the rest energy times 249. So it's 259. Now, what is the rest energy of the electron? We know that the rest energy of the electron is 0.511 MeV, which we already calculated in another problem. Okay, I think in video number 4 or number 3 for the relativity. So this means that the kinetic energy will be 127 times 24 MeV. This is the kinetic energy for the electron. The second question is asking about the speed first. Now, the speed, where we get the speed, we know that gamma is 250, which is also equal in formula is 1 minus beta squared, and beta is the speed divided by the speed of light, the speed of the particle or the electron divided by the speed of light. So from this, we can easily see that gamma squared will be 1 minus beta squared. It gives us that 1 minus beta squared is equal to 1 over gamma squared. And this gives us that beta squared is equal to 1 minus 1 over gamma squared. Okay, and so beta will be the square root of 1 minus 1 over 250 squared, because gamma is, so this will give us a value of around 0.999, which means that the velocity of this electron, or the speed of this electron, is 99991, the speed of light. Okay, so now the question is about its momentum. What is the momentum of the particle? Well, we know that the momentum is gamma mv. Well, there are several methods to calculate the momentum. One of them, let's say this method is, since we have the total energy, and we have this famous equation, this is the energy that relates the total energy to the momentum to the energy at rest. We can easily see that Pt squared is equal to the total energy minus the energy at rest, everything squared, of course. So the momentum will be E squared minus E0 squared, this. Now, this quantity it's an energy. It has a dimension of energy, which the unit will be in MeV if we convert everything in MeV. This means that the momentum will be E squared minus E0 squared. And then this C will belong then into, will be brought into the unit. So the unit of the momentum is MeV per C, and then we can calculate. We know that the total energy is 250 the rest energy squared minus E0 squared. Okay, and this you can easily do the calculation. So we can do the calculation. Yeah, so you will obtain a value that is an MeV per C. So given that the E0 is 0.511 MeV, all what you have to do is to replace with MeV. Okay, there is another method. So this is one method. Let me see. Yeah, this is method 1. There is another method which can also be done very quickly. Method 2, to calculate the momentum. We know that the momentum is gamma mv. Okay, what I can do is multiply by c squared and divide by c squared. Okay, this will give me, what is this? This is the rest mass, the rest energy, the energy at rest. So E0, and then I can do V divided by C and 1 over C. Now we know that this is an energy because gamma has no dimension, no unit. V over C is beta, which has no unit, and this will be in MeV. So this quantity will be an energy quantity. So gamma E0 V over C, this will be MeV, and divided by C, which I kept here, and this is the unit of the momentum. And now I can do the calculation. So 250 times 0.511 MeV, because the rest mass of the rest energy of the electron, times beta, which I already found above. Okay, beta. Okay, and this will be MeV per C. So this is just, those are two methods to calculate the momentum given the kinetic energy or given the gamma values or the total energy. Let's go to another exercise, this one. So the Higgs boson is believed to be at the origin of particles' mass in the standard model of particle physics. It was discovered in 2012. It was detected in the Large Hadron Collider with a mass of around 125 GeV per C squared. What is its mass in kilogram? So this is a very interesting question. If you remember, we have the mass of a particle can be expressed in kilogram, but it can be also expressed in, let's say, in this case, GeV per C squared. So it can be MeV per C squared or EV per C squared. So in this case, GeV per C squared. We have seen before how to go from mass to GeV per C squared or MeV per C squared. But now we want to know how to go from this, from GeV per C squared to the mass in kilogram. So let's start. The mass of the boson, the Higgs boson, is, so its mass, it's equal, the mass of the Higgs boson is 125 GeV per C squared. So the first thing is to convert GeV to EV. So it's 125 times 10 to the 9 electron volt per C squared. Okay. Now the next step is to convert electron volt to joule. So it's 125 10 to the 9 times the conversion factor from the electron volt to joule, which is 10 to the negative 9 joule per C squared. Now, in order to convert this to kilogram, so I have to divide by c squared. So then it becomes 205, 125, 10 to the 9, 1.6, 10 to the 19, and divided by c squared. The value of c squared is 9, 10 to the power of 16. So I took the speed of light as 10 to the 8 meters per second. So if you do this calculation, the result will be in kilogram. So therefore, you obtain the mass of the Higgs boson in kilogram, which is 25 kilogram. See, this is the mass of the Higgs boson in kilogram. Okay, so in the next video, I will do more problems in about relativistic momentum, energy, and other quantities in relativity. Thank you.